In this video, we're going to cover how to find the inverse of a function. Now, this concept comes up all the time in exams, so once you understand the basics, we'll dive into some of the key questions that you'll be asked during your exam. Let's get into it. The inverse to a function is actually a type of transformation. In particular, it's actually a type of reflection. But instead of reflecting in the x-axis or the y-axis, we actually reflect in the line y equals x. This transformation is applied using the following process. For example, let's suppose we have the following linear function. First, we swap the input and the output. In this case, the input is x and the output is f of x. This next step is more of a formality. The inverse of a function is expressed by raising f of x to the power of -1. So really all we're doing here is making sure that we're using the right terminology for the question. And finally, we'll just do some rearranging until the inverse function, f to the power of -1, is on its own. Now, let's add a layer of complexity. Suppose that your function has a restricted domain, as they often do. This means that the inverse to that function must also have a restricted domain. The rules for this are actually quite straightforward. All you do is just swap the domain and range. So, the range of the inverse function is the same as the domain of the original function. And the domain of the inverse function is the same as the range of the original function. This kind of transformation comes with a restriction. F of x can only have an inverse function if f of x is considered a one-to-one function. A function is considered one-to-one if it passes the horizontal line test. If you can draw a horizontal line anywhere on the graph and only intersect with that function once, then that function is considered one-to-one. For example, let's consider the quadratic function. A quadratic is not a one-to-one function. It fails the horizontal line test. If you were to reflect a quadratic in the line y equals x, then the result would actually be considered a relation, not a function. A relation is an expression that has multiple y values for the same x value. For example, let's look at x equals 1. If you plug x equals 1 into the quadratic, you'll get the answer 1. But if you plug it into its inverse, you'll get both 1 and -1. That's two different y values for the same x value. It's for this reason that f of x can't have an inverse function unless f of x is one-to-one. That is 1x per y. The fundamentals can be straightforward, but the devil's in the details. One of the exam questions that comes up often centers around the idea that the function must be one-to-one for it to have an inverse. In this question, the first thing that we're asked to do is to restrict the domain of f of x such that the quadratic function becomes a one-to-one function. Quadratics can only be one-to-one if their domain starts or ends at the turning point. If only one half of the quadratic is present, then the function becomes a one-to-one function. It passes the horizontal line test. This means that there's actually two valid domains either side of the turning point. So which one do we choose? In this case, we're told that the lower bound is -infinity. This means that the upper bound, b, must be the turning point, which we can find by either completing the square or by using calculus. It doesn't matter what way you approach it, you should end up with the answer b equals -2. If either of those concepts were new to you, I've linked some resources in the description for you to follow up on. Now we can find the inverse. The first thing we do, swap the input and output. It's better to use the turning point form of the quadratic rather than its original form because it makes the algebra much easier. Next, we're going to make sure that we rename f of x to become f inverse of x because that's what the question is expecting. And finally, we just rearrange until f inverse of x is on its own. It's important to remember that whenever you take the square root of a number, that both the positive and negative solutions are valid. The problem is, this has given us a relation. Now this is fine if we were trying to find the inverse to the entirety of f of x, but we're not. F of x has a restricted domain. This is where we can use this idea that the domain and range swap. The domain of f of x is from -infinity to -2. We found that in part A. The range of f of x can be found by substituting in the lower bound and the upper bound of the domain into f of x. Just remember that you can only use this approach if f of x is a one-to-one function. And remember, from earlier, we actually restricted the domain to make f of x a one-to-one function. When you perform this substitution, you'll find that the range is from -infinity to 9. This means that the inverse function must be the opposite. So far, the domain is correct. We can clearly see that the inverse relation spans from 9 all the way down to -infinity. But the range isn't right. we expect to see a range from -2 all the way down to -infinity. But what we actually see is a range of all real numbers. For this reason, we only choose the negative solution to the square root because that gives us the desired range. And we can see this quite clearly if we plot both f of x and its inverse on the same axes. Another curveball was thrown to us in the 2023 Tech Active exam. First, some context. G of x has been split into two separate functions, g1 of x and g2 of x. And that split has occurred such that both of those functions are one-to-one functions. Kind of like what we did earlier when we split the domain into two separate parts. The inverses to those functions, g1 of x and g2 of x, are then plot on the axes using dotted lines. What we aren't told is what their equations are. What we are told to do is to find where these inverses intersect the original function g of x. We can find the intersection of any two curves by equating the equation of the first curve with the equation of the second curve and then solving for x. But to do that for this question, we would have to find the inverse. And if you look at what f of x is, finding the inverse of that would be quite difficult. There is, however, a shortcut that is being hinted at us by the exam. We know that the inverse to a function is its reflection in the line y equals x. This property means that an inverse function can only intersect with its original function along that line y equals x. So, instead of finding where the original function intercepts with its inverse, we can instead find where the original function intercepts the line y equals x, and that makes it much easier. This is tech-enabled, so all you have to do is plug that into the CAS. The x-coordinates are found by equating g of x to x, and then solving for x. And the y-coordinates are found by substituting that result back into g of x, or y equals x. One of those functions is a lot easier. And that's all there is to it. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.